Okay, shall we see about getting started, or does anyone want to continue the break for a little bit longer? No objections. Let's get started. Right, hello. For those of you who don't know me, I'm Andrew Cooper. I work for Citrix on the XenServer project. I work in the Ring 0 team, generally doing hypervisor stuff, and I also have a few roles within the community. Today I'm here trying to extol the virtues of testing. Now, everyone loves testing. Customers certainly prefer if things do actually work. As a quick show of hands around the room, who's ever had a bug fix and decided it was so simple it must obviously be correct? Okay, for those of you watching on YouTube in the future, that was pretty much the entire room. What about this one? I've only got time for a small dev test. I'll get something sorted later. Yeah, most people as well. What about, that's too hard. It'll be fine, right? Yeah, as I thought. So, who actually likes testing in their respective jobs? In XenServer, it's kind of interesting. We've had a fairly diligent approach to at least system-level testing. So our infrastructure for installing XenServer, installing Windows on it, doing some migrations is very good. But individual testing of small bits of the x86 architecture, or generally the corner cases that fall down, is a little bit terrible. As a result, testing is always a lower priority activity than people would like. It's always the last thing to get done, which means it's always the first thing to get pushed to not being done. And that's actually worse in an open community. And at least if you've got a boss and your boss tells you thou shalt do some more testing, it tends to get done. It's rather less so for open contributions. So ultimately, the problem is that testing is hard. I mean, it really is hard if you don't have some good infrastructure for it. And, well, the two main problems are down to writing the tests themselves, which, frankly, is a skill to learn. It's not terribly hard, but a lot of people don't learn it. The other thing is, even if you do go to the effort of writing a test, automating it, how do you go about automating? You've got to start running cron or something like that. Without the infrastructure, it is very, very painful to do. Now, through the work that I've been doing for a while, and indeed help from other members of the community getting it integrated into OSS test, I think we've removed all of these obstacles. I certainly won't believe anyone who comes along with the excuses like it's too hard in the future. There's an easy 4-step guide. Who, out of interest, who has cloned the repository and looked at it? Ooh, that's a surprisingly large number of people. Right, some of you may be aware then that there's always a bit of boilerplate to write. There's a script that writes it. It's a couple of lines of makefile, a couple of lines of C. Sorry? Yes, we've already started because people were being slow. That is their fault for missing out. Then you go along and you edit your main file. That's perfectly fine. Stick a to-do in. Everyone likes to-dos. No project would be complete without make. This runs fairly fast. I mean, I can compile the entire repository in about 2 seconds. It's not very big. And there's even a script for running it to easily get results out and combine the lot. And if you follow that set of steps, you will get some results out that say everything's good. We really like that. It really is that quick to get started. I challenge anyone who thinks it's slower. That's perfectly fine to say, but step 2 might be a little bit of a large step. This is a real example of a test. I've had to tweak the formatting slightly, but it's literally that short. This tests XSA 203, which is a security vulnerability with VM-Func emulation. Before XSA 203, if you ran that on AMD hardware, Xen would fall over with a null pointer dereference, and everything crashes and it's bad. Hopefully none of that is terribly hard to read, especially if you've done kernel programming before. The one thing that might be a little bit different is the force emulation prefix. We'll get to that in a little bit. The second technical problem is to do with automation of written tests, and frankly this is even easier now. There's an easy two-step guide. First of all, you put a patch on XenDevel, and okay, maybe there'll be some nitpicking over it, some full stops at the end, whatever. And I as the maintainer, or frankly anyone else that has commit access onto the thing, can push to master. That's all it takes. OSS test will automatically pick it up and automatically start running it in regression. If the test does spot a regression, it will send an angry email and block pushes to master, and then someone may or may not do anything about it. But the point is that there's no further action required. It will just start working at that point. As with everything these days, there's an origin story. This one goes back a couple of years. XSA 106 was reported to XenServer. It was originally found by Bitdefender. They reported it to XenServer, and I started to take a look at it. And as reported, you could use the x86 instruction emulator to bypass the descriptor privilege checks on software exceptions. So the commonly known two here are int3, which is the debug trap, and the general int media. So int80, for example, is the legacy syscall vector. int82 is the legacy hypercall vector. There was also some rather hastily put together Windows code that would cause a BSOD. And looking a little bit closer at it, the emulator did absolutely no checks at all. We like that. You occasionally miss a check, it's all fine, right? There are a couple of other things that are important to check, the descriptor type present bit, but the key problem here was that we were using the wrong hardware mechanism. With VTX and SVM, you've got various ways of injecting events. You can specify that it's an external interrupt, hardware event, software event, and the hardware will do different checks based on that. And the problem was that the emulator for software events was telling the hardware it was a hardware exception, and that skipped most of the checks. Of course, that's easy to fix. You change it from software events from software event to a hardware event, and you recompile the code, and it works perfectly, right? Yeah, that changed the BSOD. It didn't fix it. At this point, booting Windows and having it crash was not necessarily a very effective way of doing this. So I thought I needed something easier to work with. Linux itself doesn't actually like you playing with the IDT too much under the feet of it. So instead, I turned to HVM Loader, which the code is certainly not wonderful, but as a programming environment, it's great. It's very easy. I basically deleted most of the BIOS-related code, added in some IDT handling, and that was mostly it. Now, the way to exploit this in the x86 emulator to start with involved a race condition between two CPUs, and of course race conditions are racy and they're not nice for testing with. So I borrowed a mechanism from PV guests. Architecturally, the CPU ID instruction doesn't trap, which means that PV guests get to see the real hardware information rather than the lies it wants to hear from Xen. The way that got fixed was with a mechanism called the force emulated CPU ID, which is a UD2 instruction and then Xen followed in hex after it, which disassembles moderately nicely. And then a CPU ID, which the undefined opcode handler in the hypervisor knows how to emulate. We say, that's a guest doing CPU ID. We fill in some numbers, we tell it some lies, give it back to the guest, and everything's perfectly fine. I borrowed this and added it to HVM guests to allow us to essentially test arbitrary instructions in the emulator without having to resort to race conditions. And this was a lovely mess, but it did work. The other thing discovered whilst doing this was that the semantics were wrong. In x86, traps have an exception frame pointing after the instruction, and faults have it pointing at the instruction. And if you get this wrong, you get to an infinite loop, because you trap out pointing at the instruction, go back in, re-execute the same instruction. So very quickly, my code had to be able to deal with infinite loops. So I did that. Some other quirks that appeared. One of these instructions, ice breakpoint, is an entirely undocumented instruction. It's about the best known of the undocumented x86 instructions. It always bypasses the descriptor privilege level check, and it also sets the external bit, which is normally reserved for things coming in from the rest of the system. That's okay to deal with. It turns out the behavior is actually quite similar between Intel and AMD processors. And of course, that's all working fine, and you put it together and it doesn't work on AMD, unfortunately. It turns out that the SVM injection is a little bit more complicated. We need to emulate it in a couple of cases. That actually resulted in, I think, one of the first corrections into the AMD manual. They expected IceBP to work with NRIPs, and it turns out it still doesn't. Then, about a month later, XSA 106 was released to the general world, and that's it, right? As a quick question, who has ever spent a large amount of work getting a test working and then thought to themselves, I really ought to automate that? Anyone? And oh, surprisingly few. Okay. Yes. Fast forward a bit of time to November 2015, we had XSA 156. Now, XSA 156 is a rather nasty pipeline bug in both Intel and AMD processors. If you stick a data breakpoint on the breakpoint IDT entry and raise a breakpoint, you suffer a data breakpoint whilst trying to deliver a data breakpoint, and the core goes a little bit crazy. Equivalently, if you have a user space alignment check handler with a misaligned stack, then you suffer an alignment check trying to deliver an alignment check. And in native, this is perfectly fine. An operating system can be trusted not to do that to itself because it's counterproductive. Unfortunately, this also locks up a core in non-root mode to the point at which you can't send NMIs to break it out. The solution is to always intercept these at the hypervisor, so there is at least a software workaround. But all the intercepts have fault semantics, not trap semantics, so we unfortunately released an XSA that was entirely buggy. The next time a guest ever used a debug breakpoint, it caused the guest to fall into an infinite loop. And that was particularly annoying because I really should have got around to automating it earlier, at which point we may have detected that before it went out. So at this point, you could well be wondering what exactly the XenTest framework is. So it's a number of things, the first of which is a microkernel core. So you get a file, you compile it, it's got some startup routines, does page table, exception handling, console, things like that. There are a number of bits and pieces in the library that basically anytime I find two tests doing the same thing, I move it into library code, and if most of the tests are doing the same thing, it goes from non-essential to essential library code and just gets done on boot anyway. The other thing we've got is an easy way of reporting in a uniform manner. The other thing that I found a problem whilst doing the original bit of XSA 106 work was keeping track of the various different kinds of guests. 32 and 64-bit guests behave differently, particularly in the emulation we had to do for AMD processors, and I spent far too long accidentally compiling it in the wrong mode, then forgetting which one I'd done. So when putting this together, I decided it would be easier just to let the build system deal with that and make several microkernels. So as you saw in the example to start with, you take one single file and it gets compiled multiple times to particularly named microkernel binaries, and everything's great. You can choose There are 6 variations in total at the moment. You can choose between PV, HVM, 32 or 64-bit, and the various paging modes. You can choose 1, 2, or all of them, depending on what exactly is being tested. Next thing we've got is a script to run from DOM0 to easily run a whole load of tests. It's got the test index. It's also scriptable, so that's how OSS test uses it. It essentially reports back via exit code, and OSS test knows how to turn that into the generated report it's got. The other bits you've got are a suite of tests. So you clone the repository, it's got a whole load of tests in it. At the moment, they're mainly limited to functional tests and XSA exploit tests. Other categories can appear as and when they're needed. But the important bit from my point of view is the fact that it's quite quick to run. At the moment, we've got 62 microkernels, which I think is 36, 37 unique tests. Running them all sequentially currently takes 7 seconds. The other thing that's great about this is because they're so small, I've got an edit compile test cycle of around about 10 seconds for making a change, deploying it to 5 servers around the world and collecting all the results back. Particularly when you're doing low-level x86 stuff and you want to test on old and new Intel, old and new AMD. rsync and distributed shell are great for getting this working. So we can look at some examples of the tests we've got at the moment. CPU ID faulting is one of them. The people from the record and replay project wanted to offer CPU ID faulting to the guests because for their use case they want to record the CPU ID information given to the process so it can be echoed back again in the future to cause the running of the process, running of the replay to be deterministic even if you move between CPUs. The test for that is fairly short. It's a comprehensive test of the behavior, enabling it, probing for it, disabling it, whatever. As a result, any changes to the CPU ID faulting logic or CPU ID handling in Xen is very easy to do. I think one of the changes for HVM guests was about 14 minutes between me having an idea, writing it down, compiling it, testing it, and sending it to XenDevel. I think it wasn't much longer after that that it got committed. That was only possible because I had entirely full confidence that the tests knew everything or were testing everything. This is a rather more recent example. This was unfortunately a regression we found very late in XenForm 9. 32-bit versions of Windows, it turns out, occasionally use NMIs for interprocessor interrupts. It also uses task gates for handling NMIs. And we had a bug where if that hit in user space, then the VM crashed. In this case, the test sets up the scenario and runs. It's got various quirky corner cases of the x86 architecture, but hopefully that will never break again. This is the example we saw before. It's 12 lines of code. Separate one here, this is XSA 186. This was another instruction emulation bug. It resulted because of a bad truncation on the instruction pointer, at which point you underflowed the index into the cache and copied the guest instruction stream over a user-controlled part of the hypervisor, and of course bad things happen. This test was a little bit surprising because I was running it was running in automation, and occasionally it would crash. It crashed in a rather weird way. It turns out it only ever crashes on Broadwell processors. It crashes claiming that, well, you take a page fault claiming that page is not present. Now, I've spoken to Intel about this. They say they've managed to reproduce it, and they'll get back to me at some point. So hopefully they'll get back. But this was, you boot it, and 299 and 300 times, it works perfectly well. It works perfectly well on all other hardware. but it was entirely by chance I managed to catch it. This is a rather larger test. It's unfortunately been around for more than a year. It's still not quite complete. This is the page table emulation test, which has slowly been making the rounds. This started with XSA 176, where I was trying to put together a test for that, and I booted the microkernel, and it just stopped, mysteriously. I thought, okay, I've clearly compiled something wrong, delete everything, clean the system, reboot, restart it again, and it ceased executing again. Now, as it turns out, pulling at that thread, there were quite a large number of page table bugs in Xen. So going back to the handy let's test everything against hardware, this test sets up every single unique combination of page walk that at least I can work out from the manuals describing how it works. On a Skylake system with protection key, this is 2.2 million unique page walks, and it runs in 4 seconds. That's an excerpt from, I ended up sending a patch to XenDevel, a thing titled simply Rewrite the Page Table Walker. Now the final entry there is the important one. What had happened was that there was a bug on the page tables when Xen walked them for emulation. It aliased the signal for the page being paged out by the paging agent. So what happened was Xen said, the page isn't present. I will go and ask the paging agent in DOM0 to do something. And of course, that's all void functions. You go down and right at the bottom it says, there's no paging agent in DOM0. Oh, well. So the guest got descheduled, waiting for something that will never come back to it, and that was a little bit embarrassing. So this test is still under development. Most of the code is in Xen 4.9 now, so at least that should hopefully be correct. There are a couple of remaining bugs. On Intel, we still leak the no execute bit from Xen's context into guest context. That's unfortunate because it changes the behavior of the page table error code from the guest's point of view. Also, surprisingly, it turns out the latest generation AMD processors don't order the access and dirty bit updates with respect to load. So if you go and look to see whether an access bit is set, i.e. the hardware loaded it into a TLB, you may not actually see it set even though it was loaded into a TLB, and yeah, turns out the only way to fix that is to use Comp Exchange to read your page tables, and that's going to be a moderately large performance hit to get right, but we're going to have to do it. That's how the hardware behaves. The other thing that turns out is that Intel's and AMD's implementation of SMAP is different. So we're also going to have to code our way around that. So that's a brief overview. Of course, in the copious free time that I have plenty of, there are some further ideas. At the moment, the microkernels are, you boot them, you wait for it to do stuff, and at the end it will say success or failure, or the XTF runner in DOM0 will also detect whether it crashes, so crash is also an available output. And that's what it is at the moment. It is very effective for a lot of the tasks we've got, but there are some things we could try and do better. So one example I was thinking of was having some of the test code in DOM0 play the part of QEMU or play the part of the introspection agent. At this point, you've got two halves to a test. One's the microkernel doing a set of actions. The DOM0 side can check that the correct events come through on the respective rings. It can put responses onto the rings, and the microkernel can then check that the correct action appears. That's a whole lot easier than having something that involves Windows and a whole load of proprietary code. Particularly, it allows us to test some of the more awkward emulation corner cases. We know, for example, there's a whole load of problems to do with running a rep MOVS over the MSIX table, which gets tweaked every once in a while and different bits fall off. So it'd be nice to do something better there. Configuration testing. This is one that actually came up fairly recently. Excel config files have a whole load of options in them, and you could be forgiven for thinking that some of them actually work. It turns out some of them don't. Particularly the no execute and PAE bits are wired into dev null. You can set them in the config file and it will have no effect on what the guest gets to see. So in this scenario, you could have a microkernel that can report back on each of the config options we care about. You iterate over 2 to the n config options, boot the microkernel each time, and check that as you change the config option, the change is reflected in the guest. So that seems like a nice idea. Another thing I've been looking into a little bit is to do performance testing. Now, everyone likes network throughput, disk throughput, and that's great from the point of view of running full-blown OS, but it's not terribly good at saying, I'm making a change in the hypervisor, how has that affected interrupt handling or things like that, whereas a microkernel should be very, very good at getting that, so there's nothing else to get in the way. The other thing that it turns out is great to do is to try and boot 1,000 of these domains and watch Zen cry as a result. But that's useful for doing scalability testing. How many VMs can I sensibly run on a system like this? Another area which I really like to try and do is to sit down and use some coverage data to try and work out which new bits to put into the test. If, for example, you're going along and you're trying to Right, let's switch to a different microphone, work that one out later. Yes, if you're trying to work out what's going on, there we are. Yes, the coverage, if, for example, you're testing, say, the event channel hypercalls, and your coverage comes along and says, that's fine, you took the success case everywhere, you probably find that 90% of the code in evention.c didn't get covered because you didn't hit various of the error cases. So I think that would be a useful way of testing. Now, there are some links. I'm not going to go through all of them. Any questions? What? None at all?
None at all?
Hopefully everyone understood.
So this isn't really a question. So the idea is that you just mentioned the coverage-driven thing. Yes, it's on my radar. But there's a lot of things that I need to work on before I can get to that. And if people want that sooner, they should come and help. Come to ZenDevel and find me, or send me an email.
So, Andrew, it looks like most of these tests are synthetics and only for the base functionality of hypervisor. But what about the tests of full-scale guests, like Linux running on the Xen or Windows running on the Xen? So do you plan to add something like this, or?
Well, that OSS test
so
already.
It's mostly for OSS test, yeah?
Yeah, OSS test already does that.
Well, not. Okay,
fundamentally, you can't have a microkernel-based testing scheme that's testing Windows or Linux because they're not microkernels. The point of this is to test the bits that you can't do by installing Xen or installing Linux and checking that they still function. That's still important testing, but you can't test everything like that.
So I was wondering if the XTF has any scheduler in the microkernel? I mean, if the page table switches.
No, there's absolutely none of that. It's all single-threaded at the moment. Of course, you could add that in if you wanted to. But generally, it's not very helpful for this kind, or certainly I haven't found it very helpful for this kind of tests.
Okay, thank you.
Lars.
So some of the problems you kind of found using your test framework they seem quite sort of severe problems. Do you know why OSS tests didn't catch them, or was this before?
What do you mean by which problems?
Like some of the page table walking stuff, right? Like that sounds quite we should have been hitting it all the time. Or
well, okay, if you go back and take a look at that, most of them are actually in weird-ass corner cases that people don't actually use. Now that covers, so for example, by the time Xen came along, no one was ever using PSE36, so it's not as if it's terribly surprising that the Xen code for PSE36 didn't work. PAE was also a big thing, so most of the two-level stuff didn't work. The four-level with Page Global was a little bit weird. That was the first difference I found between Intel and AMD processors. But again, no operating system would generally set that up because it's not a useful thing to do. A lot of these I only found because I insisted on testing everything the spec allowed me to, not everything that commonly gets used.
In part, this represents a bit of a shift, because I think when Xen was first written, and I think the way a lot of people start to write these things is they say the main goal is to get real operating systems to function properly and securely. So basically, if 6 years ago when they wrote the shadow page table code and the page walker and this kind of stuff, it's like, well, does Linux work? Is it secure? Does Windows work? Is it secure? Does FreeBSD work? Is it secure? If fine, then we're good. And in a sense, in starting to write these tests, Andy sort of shifted to, we want to be as architecturally correct as possible, which is probably a good shift to do, but I mean, both I think make sense.
And bear in mind that with PV guests, you didn't need any page table walking at all. You let the hardware do that for you. It's only with hardware vert, where Xen's now having to fill in around the sides, that these actually start to become problems.
In a way, it almost sounds like it's more of an architectural compliance, you know, like how compliant your hypervisor looks to the guest as the hardware looks to the host.
Yeah.
That's
it would be lovely if hardware matched what's in the manuals a little bit more than it currently does.
So if I can ask a question, because there was a lot of interest in sort of other slightly parallel sort of sections about having better, basically what everyone does is take Minios and then like lop off most of it to create their own sort of fork of microkernel stuff. Do you see an opportunity for some of the infrastructure that you've written for XTF to be sort of a base layer for a better division of library stuff so that people don't have to?
Yes, so I believe Jürgen already nabbed some of the XTF code to go and replace what Minios does with its GDT handling. Because what it did at the time was rather terrible. XTF is specifically BSD licensed, not GPL licensed, so we can go and do that. It does mean you can't blindly copy code from Xen into it, but there are ways and means to make all of this work well.
Is there any multiprocessor support in XTF?
Yes, in a devel branch of mine.
Okay.
It's on the to-do list. I've got something like 100 various branches of things that I'd like to get around to Upstream. Basically, at the moment, functionality gets implemented on an as-needed basis, which is usually oh crap, there's a new XSA. Okay, I need to write this bit of code to get it to work. For a lot of this, yes, I do have some code. So, for example, one of the things we found with introspection is that the Comp Exchange emulation is, well, broken, to put it kindly. So I do have a test that spins up 8 CPUs and then emulates Comp Exchange on all of them at the same time. And at least in the case we had, when you run all of those concurrently through the emulator, you could get 5 out of 8 Comp exchanges appearing to take the same spin lock at the same time, and that's not great. So yes, I do have code for that. I do intend to make it work in a slightly less hacky way.
All right, since we're done. Cool, thank you. We have 5 more minutes for the next session now. We're perfectly on time.
Oh, wow.
Thank you.
That's a good move.